So in the last lecture, we discussed some models which gave rise to this long-range entangled states and topological order. So today I'm going to discuss some kind of macroscopic or maybe mathematical theory for the topological order. So the mathematical theory turns out to be so-called a category theory. So the question is, why do we want to know about the category theory, in particular the higher category theory? It kind of sounds scary, but remember this. Our motivation, maybe one motivation, is to study gapless state which have an emergent symmetry. But the emergent symmetry is very general, and usually they are not. In general, they are not described by a group or higher group. So there's all kinds of emergent symmetry, all kind of anomalies. Things became very complicated. So it turns out that the topological order in one higher dimension happen to be the right theory, which is describing those generalized symmetry. So therefore, it's kind of amazing that the study of a topological order became a study of symmetry. You know, this is a recent realization. These two things maybe is almost the same thing. Okay, so more concretely, the topological order in one higher dimension, like n+1 dimensional space, is described by this so-called braided diffusion n category. So 1+1 dimensional space is a braided diffusion n category. So there's a shift. And then this, because topological order describe symmetry in one lower dimension, then we say that this so-called braided diffusion n category happen to describe a symmetry in n-dimensional space. So therefore, this braided diffusion n category somehow replace a group describing symmetry in n dimension. But this symmetry can be generalized, etc. And so then we say that a gapless liquid in n-dimensional space are described by this symmetry, emergent symmetry. Then you can also say that, yeah, these gapless liquid states in n-dimensional space are described by this braided diffusion n category. So this is why one study braided diffusion n category. It's a mathematical framework to describe the symmetry, and maybe become mathematical framework to describe this gapless liquid states. And so actually, I don't know much about this fusion category, higher fusion category, but so I can only give some kind of bare minimum. And the thing that I try to give a version which is describing those category theory using numbers. You know, usually the standard way to describe category theory are given by point and arrows and arrow of arrows. You know, those kind of things. But there's a more quantitative way to describe it. So from this beginning, we have this idea using grounded degeneracy to describe this topological order. So in a sense, at this level, the topological order are described by a sequence of integer. You know, on different manifold, there is a different degeneracy, and the sequence of integer would like a numerical way to describe a topological order. But certainly, these sequence integer don't have enough information. There's one need more data, more information, just beyond this, just a ground state degeneracy. So how to extract more information? So this more information is obtained by considering so-called moduli space. Okay, moduli space. The moduli space basically is just a space of a coupling constant. You know, from kind of symmetry, just space of coupling constant. But however, it's not arbitrary coupling constant. It's a coupling constant such that it gave rise to the gapped Hamiltonian. You know, when you have some coupling constant, your tonal coupling constant may go through transition. The thing became gapless. Then we should remove the gapless point. So those gaps are all removed. And after removing gapless point, then this space of a coupling constant may have a non-trivial topology. You know, certain part cannot be connected to other part because you have to go through the gapless point. And so this is so that's basically the modular space. But this is too general, so I don't know what to do. So here one makes some kind of logical or illogical step. That is we view this coupling constant as a metric. So in the manifold they have a metric, and then we view this matrix manifold, pretend they are coupling constant. So this is reasonable when you have a particle moving in a free space. This mass can be not scalar, can be a matrix, and the mass matrix really play a role of this metric. So in some sense, you can view this metric as some kind of mass matrix of the particle with interaction and etc. So certainly this is a jump, but doing this, I can make connection to some mathematical theory. So therefore, this moduli space in this sense became a space of a metric in a manifold. And certainly, choosing different coordinate gave you different metrics, but those different metrics was viewed as equivalent. So up to equivalence of coordinate transformation. So this became more like the mathematical definition of moduli space. Is a metric, is a space of a metric up to this equivalence relation by the coordinate transformation. Okay, but in condensed matter, we pretend this the space of a coupling constant can be modeled by this metric. So this is one assumption we make. Okay. Then once you have this space of a coupling constant, then you have this ground state degeneracy. Then we have a fiber bundle. Basically, for every coupling constant, you have degenerate subspace of a ground state subspace. And when you're changing coupling constant, this subspace is rotate. Okay. And this really became notion for fiber bundle. I think nowadays maybe fiber bundle became more popular because of the topological insulator, in the sense that when you study semiconductor, we study this dispersion relation a lot. And but dispersion relation of electron band only captures some information. The more fuller information is captured by consider the dispersion relation energy is eigenvalue. Then for every eigenvalue, you have also eigenvector. We're changing momentum wave vector in the Boolean zone, the eigenvector may twist around. So therefore, this every energy band is not just dispersion relation. Actually, it's a vector bundle over the Boolean zone. The fiber is this eigenstates, and the basis space is a wave function or wave vector which parameters a Boolean zone. So here is very similar. Here our base space are labeled by parameter in the Hamiltonian, just coupling constant. But the fiber is a degenerate grounded subspace. That's a fiber. So we really have this fiber bundle. Okay. So actually this fiber bundle really capture a lot of information, and so this became one way to describe this topological order. Is really that it's a fiber bundle over this moduli space.
Okay.
Yes.
So here the GID is something like a metric.
Yeah, it's like a metric. Yeah. Actually, I hide a lot here. Actually, yeah, there's something kind of. This is quite a jump from coupling constant to metric.
Yeah, but if it's a metric matrix, it's symmetric, right? Yeah, this GID equal to GGI.
Yeah, it's the metric. So it's the metric. Yeah. So actually, to do this, actually, you can think about the quantum Hall states. The quantum Hall states have a mass matrix. The mass is a matrix. Then the interaction potential depend on this the length measured by this mass matrix. You can present the mass matrix which have spatial dependence mass matrix, and this mass matrix define the metric. Then the interaction is given by the distance measured by this mass matrix. So this way you can make a quantum Hall states into something like only depend on the metric in the space time. So that would be the more precise analog. But here I claim any other system somehow at the long wavelength became something live on the manifold. And so the metric is the important information. That's a big thing. That on the lattice you have a lot more information, but why at the long distance we get a field theory which only depend on space-time manifold? There's a big jump, and I think that's the liquid assumption play a role here. If your lattice model is a fraction, then this step would fail. But if your ground state is not fraction, it's a liquid state. The liquid means that at the long wavelengths, you only remember the metric of a space-time. And somehow using metric of space-time to simulate the coupling constant, this is reasonable. So that is but there's a lot of jump here. Yeah.
So like for reference system, for example, the simplest example, if you have block electron.
Yes.
Can I think about the mass matrix of the block electron?
Yeah. On the lattice, you can see the lattice may not be isotropic, and so they have mass matrix. When you deform the lattice, then the mass matrix deform. So that's like the space-time have a non-trivial, non-uniform metric. So they're like curved space. So the deformed lattice really simulate the curved space. So here we're using that language. But indeed, you can see near bottom band, the only thing you worry about is the curvature. And the curvature is a symmetric matrix, which really play a role for metric of space. So it's in that sense, somehow only metric space survive at the long wavelength limit. Okay. And so now the question became how to describe this topological order. They say, okay, we want to describe this vector bundle. Okay, now how to describe vector bundle? Then the first thing is the barrier phase. So here what we describe is the barrier phase, which called the U1 connection. That's a more formal name. And the barrier phase is really this, because so here on the sphere, every point of sphere we have a tangent space, which is two-dimensional space. That's a fiber. So tangent space on the point of sphere is a fiber. When moving around the sphere, we can try to do the parallel transportation. We try to keep those basis vector parallel as much as possible. But then because sphere have a curvature, you can see that do this parallel transportation around the loop. Then this long vector and a short vector get rotated. So there's some non-trivial rotation. So this really reflection of curvature. So this also is one way to say the barrier phase. So this 2D vector rotated is O2 rotation, so the U1 phase. So this rotation represents the barrier phase. So basically, is that so we have similar thing. When you go around this coupling, when you're changing the coupling constant slowly, this ground state subscript should try to rotate. But we try to keep the basis. We pick a basis and try to make sure the basis almost parallel. But when you go around the loop, you find that the original basis vector maybe rotate into another basis vector. So two basis vectors in general differ by a unitary transformation. So this is called the holonomy. So that's one key factor of vector bundle. When you go around this coupling constant space, the parallel transportation may generate a unitary matrix. But here there's one very important thing. That is if your ground state degeneracy is topological, this unitary matrix actually is diagonal. They only have U1 factor, don't have off-diagonal factor. And there's argument about this because suppose this when you go around the loop, a contractile loop, and this unitary matrix have non-diagonal elements. Then you can imagine you're doing this atomic physics experiments. You're changing the parameter, you have time-dependent parameter, just go around the loop over and over again. Some kind of Fourier situation. And then in atomic physics, there's a standard technique. When you have this periodic motion at the over a long time, you can view this periodic motion as some effective Hamiltonian. Okay. Then if this periodic motion, this small loop generate non-diagonal unitary matrix, then that means your effective Hamiltonian of this small loop can split degeneracy. That is key. But here we already say that the topological degeneracy is robust. Those degenerate ground states cannot be distinguished locally. So any local Hamiltonian cannot distinguish them. So that means that when you go around the loop, the ground degeneration cannot be split. So that can only happen if this phase factor is a pure Yuan phase. So this is so this relates to the degeneracy. So therefore, it's pretty simple. So it's really a Barrier space, just Yuan phase, not non-trivial, non-abelian Barrier phase. It's just a U1 Barrier phase. So it's kind of like this topological insulator. And and this Barrier phase actually have a connecting to a topological term we're familiar with, because when you're changing parameters slowly go around the loop, you're actually computing a path integral and then computing this partition function. So this phase factor we described actually is a phase factor in the partition function. So this effective partition function, effective theory, would contain this phase factor. And so basically really this. This partition function basically leading terms given by this the energy density times space-time volume. That's the leading term in the partition function. Then when you have a time-dependent parameter, there's a Barrier space. The Barrier phase appear as this sub-leading term, some purely a phase factor. And in this fiber bundle language, this Barrier phase have a name, because here when we're changing coupling constant, we can imagine we are really changing the metric. So the GI background GIJ is changed. So therefore, this time-dependent change of metric give us a space-time manifold, curved space-time manifold. And in this curved space-time manifold, we can define something called the gravitational Chern-Simons term, depending on the curvature, something like actually like a Chern-Simons term. Okay, so this curvature we talk about, this Barrier space in the coupling constant really means that we have a gravitational Chern-Simons term. If you have that, you have a gravitational Chern-Simons term. And the coefficient of a gravitational Chern-Simons term is quantized, just like an ordinary Chern-Simons term. Their coefficient is quantized, actually it's a rational number. And so this number with some unit is called the central charge C, or chiral central charge C. Okay. So this is one way to characterize the gap state. The gap states have this Barrier phase in the parameter space, and this Barrier phase in the parameter space is given by this gravitational Chern-Simons term. Okay, and so this will be one data to characterize this topological order. And amazingly, this seemingly abstract Barrier phase have very important consequence at the edge. So when this topological order have a boundary, you may have a boundary gapless mode, and so therefore this so-called central charge. The central charge is basically just a number of right moving or left moving edge mode. Yeah, when you have a phonon moving to the right, you have a central charge. This phonon excitation, this mode give us a central charge 1. It's normalized this way. And then because when you have a phonon, you have in one dimension, the heat capacity will be proportional to T, and also one-word velocity. The coefficient is 1 for the phonon. But in general, for edge mode, the coefficient may be 2 or maybe 1/2, things like that. And then this is called formally called central charge. So the total heat capacity is a contribution from the right mover and the left mover. So you have the linear T heat capacity. So this central charge is just really linear T heat capacity. It's just a fancy way to say that. But this coefficient somehow appear here. There's a little bit of subtlety that the coefficient appear in the gravitational Chern-Simons term actually is not the sum of a right mover and the left mover. It's a difference. So this chiral central charge is a difference of right mover and the left mover. And so this is something quite amazing. That is because of this central charge CR and CL is a boundary property. But however, their difference is not boundary property. Their difference is the bulk property. The difference of a right-moving central charge and left-moving central charge determines the bulk topological order. No matter what you do to the boundary, no matter you can make phase transition to the boundary, you never change this CR minus CL. So this is something quite amazing. That is the boundary property is determined by the bulk topological orders. So that's in line that certain symmetry determine Lorentz dynamics. Also here, the bulk topology determine boundary dynamics. And so there are certain feature which is totally dependent by symmetry or bulk topology order. So this CR minus CL is one such feature. And this one can be measured by the thermal Hall conductivity, which you mentioned a little bit last time. Okay. So this is so there's a barrier phase of the central charge factor. And actually, what is more important is another one. Is that sometimes the parameter, this moduli space of a coupling constant have a non-contractile loops. And around these non-contractile loops, then this unitary matrix can be non-diagonal. Yeah. And so this non-diagonal unitary matrix would carry more information. Okay, what I try to say is that at the beginning we don't have a ground degeneracy, just a sequence of integer. Then by study barrier phase, we get one rational number C. Okay. Now by going through this non-contractile loop in the coupling constant, we get a unitary matrix, like even more data. So those are data to describe this topological order. So how to have a better understanding of the this unitary matrix? So here I try to let's assume space is a torus, and I try to draw a loop, non-contractile loop in the moduli space. What is a non-contractile? How to imagine there's a non-contractile loop in the moduli space? Okay. So here a path is I deform a torus from here to here. So this is like a path in the moduli space. I deform a torus. Okay. And then when you come back to my older torus, then we just glue this boundary to this boundary. Then we get this path. These two boundaries are identified. But to get a non-trivial loop is such that these two boundaries can be identified through a non-trivial map. There's many different ways to map a torus into a torus itself. And so one way is to do this 90-degree rotation here. That's called the S matrix in 2 dimensions. Or you can do this Dane twist. You can shear deform the torus until to get this shape. And this shape and the original shape can be identified via this coordinate transformation in this graph. So this is an example of this non-trivial map. So this non-trivial map from the space to itself is called the mapping class group. So they form a group. Okay. So this is the point that this non-contractile loop in the moduli space is given by the mapping class group of a space. Okay. So this pi1 is non-contractile loop is mapping class group. Yes.
Why doesn't the Floquet argument work when you have a non-contractile?
Okay. Yeah, that's a very good question. So actually, Floquet argument also works here. But if you go through a non-contractile loop, you will split degeneracy. And so through the contractile loop, it's more like a perturbation. You can do a big loop, you can do a small loop, but small loop is like perturbation. So for the perturbation, you can never split degeneracy. Actually, when you do a non-contractile loop, you will split degeneracy. So this is actually important. I mean, so right now when people using this ground degeneracy as a protected qubits to do quantum computation, if your space don't have a boundary, you don't have a quasi-particle, then you can do this kind of non-contractile loop to do this computation. So then the issue is that whether this unitary matrix is powerful enough, their product can generate a dense unitary matrix. You know, for every non-control loop, you have a particular unitary matrix. Well, the combination of them give you a dense set across any unitary matrix, so that became universal computation. So it's a similar, yeah. And so this large loop really may correspond to large perturbation, so not small perturbation. So then you do split them. Okay, so the point is that you know, so this non-abelian barrier phase, actually there's a formal way to say that it's they form a representation of a mapping class group. Okay, so so the mapping class group representation, or more precisely, is a project representation of mapping class group. Is another data in addition to ground state inertia, in addition to this non-abelian barrier phase, there's additional data to characterize topological order. So basically, we're mainly thinking about this mapping class group representation, which actually can be quite complicated. But however, if our space is a torus, it's easier. If a space is a torus, it's this pi one of a model space is always this SL NZ. N is a spatial dimension. It's easy. And when n equal to 1, that's 1 plus 1 dimension. In 1 plus dimension, this SL1Z is a trivial. This trivial group. And so this actually relates to the thing that in 1 plus dimension, there's no topological order. So it's consistent with our desire that the topological order are described by this vector bundle. But in 1 plus 1 dimension, this vector bundle always trivial because the basis space is trivial. And the modular space is trivial. Then the vector bundle has to be trivial. So therefore, indeed, there's no 1 plus 1 dimensional topological order in 1 plus 1 dimension. For some people who know, familiar with mathematics, there are indeed a non-trivial 1 plus 1 dimension topological quantum field theory. So looks like there's something non-trivial even in 1 plus 1 dimension. But here I want to say that this topological quantum field theory in 1 plus dimension, I think in kinetic physics correspond to symmetry breaking states. They have a grounded inertia on the circle. Even on the circle, there's grounded inertia. And so maybe this 1 plus 1 dimensional quantum field theory, topological quantum field theory, actually describes a symmetry breaking state. So this is I think what we think at the moment. And so in 2 plus dimension, the mapping class group actually is SL2Z. The SL2Z is generated by this two generator. One is a 90-degree rotation. It's like this. Yeah, we have this torus. Then we glue these two boundaries by rotating, by exchanging x and y. Then another is this Dane twist. We're gluing these two boundaries by shear deform one direction, but not the other direction. And this so-called this ST matrix. So therefore, for this kind of geometrical transformation, we get the non-abelian barrier phase is given by two unitary matrix, which is ST matrix. S for the 90 rotation, T for this shear or Dane twist. Okay, and this ST matrix generate this SL2Z representation. So in two-dimensional topological order, in some sense we can say that this topological order are quantitatively described by this ST matrix. There's S matrix and T matrix, and they form SL2Z representation. Yeah, this may be the key thing I just mentioned. Yeah, so there's that is the quantitative description of this two plus dimensional topological order.
So yeah, this parameterization of transcendent term is in the modular space. So the metric is not the real metric. It's not.
No, it's real metric. So the it's really this. So here Yeah, maybe we can discuss this.
So
So when you're deforming this when you consider loop in modular space, you actually consider a time-dependent metric. A metric in the space depend on time. And that's give you a metric in space-time. So therefore, a trajectory, a loop in moduli space correspond to a correspond to a curved space-time, a particular curved space-time. But however, this space-time have a restricted geometry. It's sigma g is a space, is a genus C Riemann surface, and time direction always pi s1. But however, something like that. That space-time have this with some curve, with some curvature.
But the G here is the real metric or it's the parameter?
It's real metric. Yeah.
So the definition is different from before.
No, it's same. It's the same. It's the same. Before, what I try to say is the following: there's a Bayer space in the coupling constant space, but the Bayer space in coupling constant space can be viewed as a passing integral in space-time. And this space-time is have a special geometry. The space is a fixed. Time is just a circle S1. So this time direction S1 in time direction correspond to the loop in the coupling constant space. So there's a translation from coupling constant space to the real space time. And yeah, this connection can be useful actually.
Physically, can I think in some different way? So I'm thinking about couple the system to the background metric. Can I think in that way? And I improve out this.
Yeah, you can think, but the metric, yeah, you can think the system coupled to the metric. Yeah, the metric is a background metric, so have no fluctuation.
So I integral out all the dynamic fields. So I just get this.
Then you get a partition function only depend on metric, background metric, and then this partition function may contain a phase factor, and this phase factor actually is correspond to the Bayer space in the moduli space when you're changing coupling constant. So there's this translation of changing coupling constant and the curved space-time. This translation between the two, and then this translation is useful because then you can using some topological algebraic topology in curved manifold, then to make constraint on the Bayer phase in the coupling constant space. Yeah, so that is a connection. Okay, so the key point here is that so when I say topological order is something very abstract. So now you can think about topological just ST matrix. That's it. Or maybe ST matrix is not enough. Maybe there's a central charge, chiral center C. So ST matrix and a C maybe is a way to quantitatively characterize topological order. Okay, and so this became very concrete. So when you're using topological to describe a symmetry, you say, okay, this symmetry are described by this ST matrix and the C. So this ST matrix just became name and label for the topological order, and also for the symmetry if we think topological order can describe a symmetry. Okay. So now let's ask another question. Whether this data can completely describe topological order or not. So there's a concern that there are two different topological order share the same ST matrix and the same central charge. Yeah. And no, actually, this ST matrix is not enough. So it's unfortunate. It's not enough. And because we only consider a torus, we have to go consider higher genus Riemann surface. There's a similar thing of ST matrix for higher genus Riemann surface. ST matrix is only for the genus G equal to 1, the genus 1 Riemann surface. Okay. And they have to consider more general marking class group. That's enough. Maybe that's enough. We still don't know. That's still conjecture. But at least we know if you only consider torus, it's not enough. But on the other hand, if it's enough in practice, because the counterexample found in this paper have I forgot 50 me see, have a lot of onions. It's a, let me see, similar to 50 square, you know. So that's a simple example. I have we know, but maybe they're simpler, but maybe no, we don't. So we have a lot of onions. We have counter example, but we don't have so many onions. Then ST matrix is enough. So so at the moment, that's how I make this practical something. We pretend ST matrix is enough. Then using ST matrix to develop a theory for topological order. The reason for that is, you know, there's a more complete theory for topological order based on the more data. But the more data is just too complicated. It's very hard to deal with. And but the pretend ST matrix is enough. Is can give you know can cover most cases. Okay. And so actually relate to Zheng Chen's question, and so this is a connection between Barry phase in the moduli space or coupling constant space, and also the space-time topology. You know, a curved space-time corresponds to a particular loop in the coupling constant space. So this connection between the two give us this constraint that the C is a central charge, is Barry phase in the coupling constant space. And the DG actually is a ground degeneracy on the GNC Riemann surface. Somehow this Barry phase in the coupling constant space and the ground degeneracy have a constraint, you know, and so this quantity has to be this product, this has to be integer. Okay. So I find this a kind of an interesting thing. It's a very different physics somehow connected. But this is really based on this picture. That this Barry phase and the space-time topology have a relation. And this relation actually is similar to the other relation in quantum Hall states. And maybe let's say for the bosonic quantum Hall states, we know we have a Hall conductance. The Hall conductance is like central charge C. It's some kind of Barry phase. That's a Hall conductance. And then the Hall conductance and the ground degeneracy are related. You know this. So actually in quantum Hall state we have a similar relation. Yeah.
But what happens for P plus and P topological conductor?
Yeah, this is for boson. For fermion, there's a different constraint. Actually, this became really interesting. And so actually for fermion system, we have a similar relation. And that relation is saturated. For bosonic system, actually this relation is not saturated. This relation is it's loose than what we know, you know. But anyway, so there's some relation. So I won't go into this. Okay, so let's pretend ST matrix is enough, you know. The next question is the following. We know that the ST matrix form a representation of the of SL2Z. Okay, so for every topological order, we have ST matrix. They form representation of SL2Z. So now we can turn the question around. Can we using SL2Z representation to classify topological order? It turns out not. So not every SL2Z representation corresponds to a topological order. Only some very special SL2Z representation correspond to topological order. Okay, so so therefore our theory for ST matrix is not so good. You know, we have a data set, but the data do not give us a description. But our data set is too general. You know, most of the data actually is illegal. Only a small subset is illegal. And so therefore, so we just say ST matrix is SL2Z representation. It's not a very informative thing to say. If you say that, then most representations don't correspond to any topological order. Only special representation corresponds to topological order. So therefore, we have to really, to understand things better, really have to figure out which special representation describe a topological order. So this really became a classification problem, how to classify topological. We can figure out the special condition on ST matrix, on SL2Z representation, then we can really obtain, we can classify topological order, making a table of topological order. So that makes this a mathematical theory of topological somehow more complete. Okay. So therefore, we need to find some conditions on this SL2Z representation, so that only special representations satisfy those conditions describing topological order. Okay. So how to find this condition? And certain one condition is this one: S squared and ST cube. They kind of equal up to this phase factor, and equal to C squared to 1. So basically, like remember, S is like a 90-degree rotation. Then S to the fourth power is a 360-degree rotation. So you go back, should be identity. Amazing thing that the ST to the cube, 6th power also is always identity. But this is defining relation of SL2Z representation. Any matrix satisfies this equation give rise to the SL2Z representation. So we need some additional condition beyond this to select special SL2Z representation. Okay. So the question is how do we find more conditions? Okay. And actually the idea is the following. So let's consider torus. Okay. The torus, then you can make can be viewed as a sphere attached with a handle. Okay, that's one way to view torus. Then you can make this handle very, very thin, handle. Then almost it's so thin, maybe you feel I can ignore the handle. Then what you have is a sphere with 2 punctures. Okay. So here I just want to, it's not something not logic. I just say the torus and the manifold with a puncture have some relation. Yeah, you can pinch out a handle, then you actually get the punctures. Okay, the puncture is like excitations. Yeah, so therefore this pinch torus and this torus and the sphere with 2 excitations somehow are related. Indeed, this is true. The sphere with 2 excitations and the torus, these 2 data somehow is very much related. Okay, and so this is the idea. So far when we consider this ST matrix, we only consider ground state. We did not consider excitation. And this relation suggests that we should consider excitation, and then to seeking more condition on this. So actually, there's a little story here. At the beginning, like in 1980s, when we try to think about this, how to systematically describe topological order of quantum Hall states, there's basically two directions. One direction is using ground state property. That's what I just described, using ground state, degeneracy, the vector bundle, etc. Another direction is using this excitation. Okay, and so at that time, I feel I'm a little bit resist to the excitation picture, and because I feel that in order to use excitation to describe a phase of matter, I cannot consider only low energy excitation. I have to consider all excitation. I find that the theory about all excitation is too complicated because the number of excitation is infinity. I have to consider infinite number of excitation. That's too complicated. So I'm thinking about this ST matrix using this approach. But it turns out that thinking about the excitation is at least at the moment we see that thinking about excitation is more helpful, and actually the theory about excitation developed faster. And so actually this modular tensor category theory, this scary name, is actually just a theory to describe excitations, you know. And so when you hear category, you say, oh, it's really theory for excitations. The higher category is just theory not only for point excitation, also for string excitation. So two category theory is for point excitation and string excitation. Three category is for membrane excitation, string excitation, and point excitation. So all those so-called higher category is just a theory for excitations. Okay. So similarly, to really obtain a more complete theory, we need to consider excitation. So historically, is that you know, we have this topological quantum field theory, which is kind of like a Ginzburg-Landau theory for topological order. You know, the Ginzburg-Landau theory is for the symmetry breaking phase. And for topological order, there's also similar Ginzburg-Landau theory. That's like a topological quantum field theory. And in 1989, you know, we can find that this topological quantum field theory have a very close connection with the conformal field theory. And then in the same year, there's a very systematic study of conformal field theory. And it turns out conformal field theory and the modular tensor category are closely related. So actually the name of modular tensor category is given in this study for conformal field theory. So that's in the early days, we see there's a topological quantum field theory or this topological order, and the modular tensor category has some relation. Yeah. Okay. So as I mentioned, that this is a modular tensor category theory, and it's basically it's a theory about excitation. Okay. And actually, we can see that the theory about the ground state and the theory about excitation have a very close connection. And the one way to see connection is through this picture. So here I'm describing this a torus, this x or y, describing a torus. Okay. The vertical direction is time direction. And we imagine on the torus we have some degeneracy. Okay. And then also you also imagine on above this ground state we have some excited state, some excitation, the type of anions. Okay. So then what is this path? This path is describing we create a pair of anion. We create a pair of anion from vacuum. And then we move one anion all the way around the x direction and annihilate them. Okay. So this is like a tunneling process by creating a pair of anion, then move anion all the way on torus, annihilate them. So therefore, this anion tunneling process is an operator which acts on the degenerate ground state, to map ground state to another ground state, to map the ground state subspace to ground state subspace. So this operator acts within the ground state subspace. Then we can do another anion tunneling like in y direction. That's this term. Then we can do the anion tunneling, the first one, but in the opposite direction. We originally create a pair of anion. We move anion in the positive x direction, but this time we move anion in the negative x direction, go backwards. And then similarly, we can do another one for the y direction anion in the opposite direction. So basically, we have a 4 operator act on the ground states. Okay. Then the magic is that we can deform this loop. We can imagine because there are 2 loops, but here we can pinch the loop. So deform the loop. So then so the first and the third anion tunneling can be viewed as a loop in space-time like this. And the second and the fourth anion tunneling can be viewed another loop in space-time like that. So we do some kind of multiplication with the anion loop. Then what is this picture? This picture basically is the one anion going around another anion by 2 pi. So this is the mutual statistics. If two anions have non-trivial mutual statistics, then there's a non-trivial phase factor. Okay. Then if you believe that, that means the application of this full operator gave rise to the phase factor. So this is a Heisenberg algebra. Basically, it's a UW equal to a phase factor times W and U exchange U and W. So first anion, this first anion is a U, a second anion is a W. So therefore, that means that the grounded would form an algebra of this representation, the UW equal to WU with the actual phase. And this phase is this mutual statistics. And we know that this algebra have a non-trivial representation, only do not have one dimensional representation. And so therefore, from here, we can say the ground state must be from representation of this algebra. So therefore, this ground state degeneracy is a multiple for Q. Q is a mutual fractional statistics, the denominator of this fractional statistics. Okay, but anyway, so yeah, this is really the simple example. We can see that the ground state picture and excitation picture are very closely related. And the so-called modular tensor category is kind of like that, actually. It's this kind of thing. But it's much fancier. They consider all kinds of braiding, not just like a two word line linked together. They can all kind of possible linking or possible operation you can do. This full theory is just this modular tensor category. Okay. I think so now we try to develop a theory for excitations. Yeah. So what is the general theory of topological excitation? Why this general theory of topological excitation is a category theory? What kind of structure do we have? Okay. The reason I'm asking this question is the following: is that for excitation, quasi-particle, we know about it. It's a quasi-particle, we deal with that all the times. And we never encounter category theory, why we need a category to describe a quasi-particle, And so here I try to do things more carefully, define quasi-particle more carefully. Then hopefully by doing things more carefully, we can see that, yeah, we need something very advanced like category theory to fully describe those quasi-particles. Okay. And first, I have to limit myself to gapless system because the following definition do not work well for gapless system. So actually, the quasi-particle in gapless system is much trickier to define. But for gapless system, it's easier. So we'll do that. So for the gapless system means we have a Hamiltonian and we have a grounded subspace. Okay, and there's energy gap above that. Then what is the excitation? What is the excitation? You say, oh, excitation is any wave function not in the grounded subspace. You can define that way. So anything here, any superposition of this will be excitation. But that's not what we mean. That is the excitation in atomic physics. But in the many-body physics, when we say excitation, there's some notion of locality. They're kind of local. It's locally somewhere. Okay. Then things become difficult. Then what do you mean by locally somewhere? So this first is pretty fundamental. That is we say the excitation is just another wave function basically. But this wave function is a ground state of a modified Hamiltonian. This modified Hamiltonian have a traps basically. We have a traps. Then the ground state of this modified Hamiltonian describing excitation located near the traps. Yeah. So those delta H describe a trap. The trap may just some kind of local Hamiltonian near a point and maybe near a loop. So this L can be a loop. So we modify the Hamiltonian along a loop. So my trap can be a loop like a trap. Then that define a string excitation. Okay. So this is defined excitation, and so actually, but here we add something extra. That is, we assume this Hamiltonian with a trap also gap, also have energy gap. So this energy gap. So there's a grounded subspace. So this grounded subspace is my excitation. So suddenly you find that that's already something quite unusual, because excitation usually means a particular wave function. But if you're using trap to define excitation, I do not specify a wave function. I specify a subspace. Okay. And this actually is important because it's kind of like using so for example we're using for electron system. Let's see what happens. We're using a SU2 symmetric trap to define my excitation in the in the insulator. Then you find whatever I trapped, either my trap don't trap anything, so we don't create anything, or I trap something, means some electron is trapped here. But because my trap have SU2 symmetry, then the trap state always have twofold degeneracy. So in this way, we do not trap a spin up or spin down electron. We trap them together. Yeah, so this kind of notion is very important. So so the internal degree freedom is hidden in this degeneracy. This degeneracy is like an internal degree freedom for the trapped excitation. Okay. And this also relates to the thing. This internal degree freedom, when can be shared to every trap, can be fractional, don't have the integer. So we can have a weird thing like that. Okay. So this is very important. We have a trap to define quasi-particle and the ground state subspace really to define the wave function. So excitation is a ground state subspace. Okay. And so then how do I label quasi-particle? It's very simple. This trap just label quasi-particle. For each trap, we have a quasi-particle. Okay. Then we are facing a problem. We have infinite number of quasi-particle. And so usually when we say we have an anion, we don't mean a trap Hamiltonian. So there's an equivalence class. So if it is trap of electron, then you change the trap a little bit. If it's still one electron there, we say they are same excitation, same type. So therefore, so next thing is that we have to define when the two trap Hamiltonian are equivalent. If two trap Hamiltonian equivalent, we say these two trap describing same excitation. So that define the type of excitation. So we need to define the equivalence. Okay. So first, so equivalence is defined as this. If you can deform the trap Hamiltonian continuously without closing this energy gap, then we say this deformed trap will be equivalent to the previous trap. If two traps can be connected by deformation without closing energy gap, then we say these two traps are equivalent. And if you can deform the trap to 0 without closing energy gap, that means this trap nothing. So that's trivial excitation. So the trivial trap means you can deform trap to 0 and you do not close this energy gap. However, if you can deform the trap to 0, you always close energy gap. So that means then my trap something non-trivial. So that's called topological excitation. Then two topological excitations are equivalent if their trap can deform to each other without closing energy gap. So that's kind of a usual definition. Okay, so this define the types, and amazingly that for topological order, there are only finite number of types of excitation, although we have infinite number of traps. But most traps are equivalent. There's only finite number of inequivalent traps and not define this topological excitation. So this is kind of formal way to define anion. If you want to define anion very carefully, using the trap, using the equivalent relation trap to define what do you mean by anion. And this definition is very general, including both abelian anion and non-abelian anion, which I mentioned in the last lecture. Okay. Then there's a subtlety. This subtlety is turned to be very important and was still kind of very uncomfortable. I think for me, I still feel very uncomfortable. The subtlety appear in the higher dimension. When you have a point-like excitation, we don't have such subtlety. But when you have a string-like excitation or membrane-like excitation, there's a subtlety. The subtlety is it looks very, at the beginning, looks like it's not subtlety. That is the trap. When you have a string excitation, my trap Hamiltonian should be a local Hamiltonian around this string. Should be local Hamiltonian. That's very natural. We will deform this local Hamiltonian. We also deform among the local Hamiltonian. That deformation class also local Hamiltonian. This seems very natural. But however, this definition have a problem. Let's assume we have a trivial product state. Then in 3 dimensions, then we have a 2-dimensional trap. Then this trap has some spin flip. Okay. And the spin flip has some interaction, has some complex hopping. Then this spin flip form of quantum Hall states. You know, they are all possible things for the local Hamiltonian. Local Hamiltonian give rise to quantum Hall states. And once you get the membrane like a quantum Hall state on the membrane, you can modify the trap Hamiltonian. Basically, you modify the Hamiltonian around the membrane. Because the quantum Hall state have non-trivial topological order, there's no way to change that to trivial without closing energy gap. And there's no way to change one quantum Hall state to another quantum Hall state without closing energy gap. Okay. So by this definition, we find that even for trivial product states in 3-dimensional space, we have infinite number for membrane excitation. Each quantum Hall state is a membrane excitation. So the lot of excitation is very, very complicated. Okay. So this kind of excitation we call the descendant excitation, you know, because they are formed by trivial excitation. In the product state, we don't have trivial particle. This trivial particle is not conserved, they can disappear by themselves. But the trivial particle can form a quantum Hall states. As a membrane station, they are non-trivial. Okay. So we feel very uncomfortable with this kind of descendant excitation. We want to get rid of that. Actually, we don't know how to get rid of that, but there's one proposal. The trap Hamiltonian can be non-local around the string. So that's different proposal, different class. We trap something, but this Hamiltonian along the string can be non-local. But however, away from the string, they are all local. So any 2 points on the string can interact. But however, a point on the string can only interact in neighborhood of a bulk. You know, that direction is local. Actually, I don't know whether this works or not. So it's just pure conjecture moment. Okay. And then therefore, we can use this non-local Hamiltonian in 1 dimension or in 2 dimensions to define our trap. Then our equivalence relation is much stronger. So any deformation among this non-local Hamiltonian is allowed deformation, which if do not close the gap, then maybe that defines this. So using this non-local Hamiltonian, we define a different thing. We define elementary or descendant. If something descendant means that we can use non-local Hamiltonian to deform to trivial, to deform to nothing. And elementary means that there is no such a non-local Hamiltonian. Even for non-local deformation, we cannot deform that way. Okay. So why we go through this? It seems very complicated, but unfortunately, this is necessary. And one way to see it's necessary is the following. Let's think about 3-dimensional superconductor, which actually is a Z2 topological order. And if you include the electromagnetic field as a dynamical gauge field, you know, 3-dimensional superconductor with a dynamical electromagnetic field is a Z2 topological order. And so actually, that's the first example of topological order. And amazingly, this Kinson-Landau theory for symmetry breaking state are developed using the wrong example. And so in this three-dimensional topological order, let's describing what happens. What is the descendant extension in this three-dimensional topological order? In one of in this three-dimensional superconductor or Z2 topological order, we know there's a Borg-Leibov quasi-particle, which is a fermion, neutral fermion. This neutral fermion can occupy a membrane and form a P plus IP topological states. So that's a kind of membrane extension. Okay. And this membrane extension, and also we can think about it along a line. This neutral fermion along a line can form this a P wave topological in one dimension. This Marana chain or PPF chain, on this one line. So that's a one dimensional string station. It's a P wave superconducting string station. And this kind of string station formed by this neutral fermions should be contract with the vortex line in the superconductor. And I claim that the vortex line is elementary, but this P wave line is a descendant. So the claim is that when you have vortex line, you cannot get rid of the vortex line by even using non-trivial non-local interaction along the line. You cannot get rid of that. That seems more topological. But however, when you have a P wave superconductor along a line, then when you this phase depends on the one-dimensional space. When you allow non-local interaction, you go to 0 dimension. At 0 dimension, we don't have a P wave topological conductor, so we can get rid of that. So that's the one thing. Another thing is the following: when you have an elementary extension like a string extension, this string extension cannot have end. For some reason, the vortex line is more fundamental in some way. It cannot end. Even though the string extension, this string extension cannot have a boundary. The boundary is not allowed. But however, for any descendant extension, it's character that this descendant extension can have a boundary. It can end somewhere. But the certain boundary may be non-trivial, maybe gapless, maybe Marana zero mode, maybe something non-trivial, but it can have an end. The vortex line in superconductor just cannot have an end. It's a very special line-like extension. It's not cuttable. You cannot cut it. And so therefore, that is this distinction. So elementary and descendant. And it's kind of important. And actually, I wish to formulate a theory for extension in topological order using only elementary extension. Because descendant, there are too many of them. Any phase of matter is a descending extension. It's too many. And since that's a kind of is descendant, that means it's not that necessary, and we can get rid of it. But unfortunately, I think in this paper we kind of taking that point of view. We try to get rid of the descendant, try to formulate a theory only using the elementary extension. And but recently there's some pretty fast progress in this higher category theory. But the one reason for the progress is that to include descendant as in a structure, and looks like if you include the descendant extension into the mathematical structure, the mathematical theory is more regular, it's better. Since I do not know the math theory, so I couldn't appreciate that point. But I was told by mathematician, yeah, it's important to include this. But I still wish I don't need to include this. But anyway, so there's this two type of extension. But however, in two Poisson dimension, we don't need to worry about the string extension, and we only need to worry about the point-like extension. So most time in this lecture, we will not discuss this string or membrane excitation. But here I just want to say that in higher dimension, we need to discuss the string and the membrane excitation. And when we discuss string and membrane excitation, then there's distinction of a descendant and elementary. And then there's a much richer structure. So a lot of very rich structure. And
can I think about this descendant state as certain type of like invertible states? Because
no, don't have to be. For example, yeah, just like let me try to see this.
Because it does not change in the ground state degeneracy. You can include it.
No, invertible state is a yeah. Some descending excitation can be invertible, but some descendant can be non-invertible. They include both invertible and non-invertible. Include both. And the example I just gave, like in 3D superconductor, you have a line, and this Bogoliubov fermion may form this pure superconductor, and that is an invertible line. That is invertible line. And but however, what's other example? Like in Z2 gauge theory, you have Z2 charge. Their Z2 charge is the boson. And the Z2 charges, as the boson Z2 charge, have this mode 2 conservation. So this Z2 charge have a emergent Z2 symmetry. Then this boson on the line may form a Z2 symmetry breaking states. And this Z2 symmetry breaking state is not invertible. So the both are descendant excitation. But the one is invertible, another is not invertible. Okay. Yeah, since you mentioned this invertible or non-invertible, I just raised one very interesting issue here. Because in the Z2 superconductor, we have the line of a P per IP line, the P with a line, which is invertible. And we also have another flux loop, a flux line, just a Z2 vortex line in superconductor. Then there's actually the issue. When you actually have Z2 vortex line, you may ask whether my Z2 vortex line contain this P with superconductor line or not contain P with superconductor line or not. And this became hard to determine, because this is invertible. So we don't see them as a degree freedom. There's no degree freedom. So actually, and also this Z2 vortex line cannot be cut. You don't see the boundary Marana zero mode. So this became ambiguity. And this ambiguity sometimes can be important because in 3-dimensional topology order, sometimes you have a line like excitation. And you also have this invertible descendant line. But you couldn't tell whether certain flux line have invertible line or don't have invertible line. There's obstruction forbid you to tell to have absolute certainty to say which one have, which one don't have. And this abstraction represents another type of topology order. So this invertible and non-invertible is actually it's very important. And also this later we'll see that those invertible line, they may describe a symmetry. Invertible line correspond to this higher group symmetry. They're invertible. But the non-invertible line give rise to non-invertible symmetry. So that in that sense also very useful. Yeah. So that's this question.
Do you expect descendant and non-descendant to be distinguished by whether the excitation can in some sense be detected at infinity?
Yes, that's a way. The elementary one can be detected at infinity, but descendant one cannot. So that's another way to do that. So if you're using this remote detection, this remote detection only applies for elementary one, and for the descendant one, they cannot detect remotely. So in some sense, you can see this is also reasoning why include descendant one. This will make your life much harder. And I'm still hoping, and I still feel that maybe there's a better hierarchical theory, not including descendant, only in terms of elementary. I'm still hoping that exists, but at the moment, the mathematicians just go in another direction.
In the case of the 2D ferromagnet, can't we consider the domain wall as
Yes.
elementary?
The main was elementary excitation.
Why do you say you can ignore string excitations in 2D and we talk about 2D?
Oh yeah, that's a very, very good question, and yeah, maybe I'll go there. Yeah, so I will discuss that. Yeah, indeed. So in D dimension, we can consider D minus 1 dimension as excitation. But why you only consider D minus 2 and lower? There's a reason to do that. Yeah. Okay. Yeah. I think I already mentioned this. Yeah. The type of excitation, just if we can deform Hamiltonian, the trap Hamiltonian without closing energy gap, then the two excitation will belong to the same type. Okay, that's very easy. But somehow we miss something. There's a simple type and a composite type, which is actually a very, very important concept. But somehow in physical theory of quasi-particles, we kind of overlook this distinction. So I'm trying to. So this is actually a very important concept: simple and composite. So what is concept? You know, here I say that we have an excitation, we have a trap, and we have a Gaussian subspace. Okay. And so let's see. So this degeneracy means given by those traps. Okay. Then we can ask the following question. Let's only modify one trap slightly. When you modify this trap slightly, the ground subspace may rotate into another ground subspace. So this is what we talk about. Is yeah, we may have unitary transformation connecting two ground subspace. But there's one more possibility. They may split. Because we may have an accidental degeneracy. That is, suppose we have a trap. We trap a spin 0 excitation and a spin 1 excitation at exactly the same energy. So my trap have a fold degeneracy. But fold degeneracy really coming from spin singlet and spin triplet. Then when you modify your trap a little bit, still maintain rotation symmetry, then you may split singlet, triplet may split. So this may happen. So in the mathematician, when the mathematician talk about the excitation, certainly never talk about excitation, they call it object. Okay. When they say the object, actually their object including this accidental degenerate excitation. So I think in physics, when we say excitation, we already assume there's no accidental degeneracy. But in general, if you do things very carefully, just do a trap, do a ground subspace, this definition includes this accidental degeneracy. And so therefore, this composite type, it just means that we have accidental degeneracy. And amazingly, that the first order phase transition is also can be as accidental degeneracy. Right at the first order phase transition, the two ground states are accidental degenerate. And this feature works for the string-like membrane-like excitation. Suppose we have string-like excitation, and one string is one phase, another string is another phase. Then we may tune the Hamiltonian on the string right at the first order phase transition between two phases. Then at that point, my string excitation is composite. Is either phase A, phase B have same energy. So that's kind of composite. Okay. So the composite really write this way. So this if alpha is a composite, it's like a direct sum of a two excitation, I and J. You know. Yeah, this thing confused me a lot because when you have a spin 0 and the spin 1 excitation, then one may say, oh, we will think a tensor, spin 0 bound state with spin 1. But here it's not tensor, it's not bound state with spin 0 and spin 1. It's a sum, direct sum And so it's really the sum. And for my own, I have this confusion before. That is because usually people don't write this as a circle with a plus. People write that as a plus. When you write as a plus, I'm thinking of what the plus means. Maybe superposition of I and j. So for a long time, I think about this is a quantum mechanical superposition. I just don't understand what this relation means. So you can imagine I have a hard time to read the GTF's appendix. We'll think that way. But actually, it's really a direct sum, and it's really this composite just accidental degeneracy. But this generalization is important in building this the mathematical theory for the excitations. Okay, so that is that's basically the main thing. And so maybe the last I will end with this fusion ring. So now we get so with those preparation, finally we can review some more sophisticated structure of excitation. The fusion ring just describes the bound states. The bound states sound very simple in physics. You have electron and proton bound state get a hydrogen atom, and that's it. And there's no big deal. But when you think about the excitation more carefully, the bound state became very tricky. So what do you mean by bound states? So bound states really means that we have two traps, one at I, another at I1, I2 have two traps. So meaning I1, I2 just two traps. Okay. When you have two traps, when you stay very far away, you can view two traps as one trap. Then the two excitation became one excitation. So that's really fusion. That's really the fusion. You know, when I say when I is one trap, J is another trap, but I tensor J can be viewed as we view two traps as one trap from very far away, and that's it. So nothing changed. It's just the point of view is changed. Okay, but there's an issue. When two trap is viewed as one trap, this single trap is a very special trap. It has two centers. Usually a single trap has one center, but this single trap has two centers. So it's a special trap. So therefore, this special trap may have accidental degeneracy as a one trap. When you view this one trap, they may have accidental degeneracy. So that's why this composite excitation became very important. So in a sense, so when the two traps are separated far away, yeah, you have a degenerate subspace. When the two traps are getting closer and they start getting mixing, they may split. They may split. So this is splitting. Then that means after splitting, this became a so-called simple excitation or a simple, not composite. So two traps is composite, and they may split, become simple. So this is really the notion that the bound state of two excitation are in general a composite. It's not like a electron proton give a hydrogen, and both they're all simple. Electron simple, proton simple, hydrogen simple. But in general, the bound state of two excitation is composite. It's really an example is like a spin on half and a spin on half. Their bound state is a composite of a spin 0 and a spin 1. So it's this. Then we have this fusion rule. The spin on half can go into spin 0, and the spin on half can go into spin 1. So this gave him a fusion matrix or fusion ring. They define the product. You know, we call this ring really that this kind of object can have the product operation, also have some sum operation. Sum of this direct sum composite operation. The product is a fusion, and then we have this operation to describing this their bound states. So the NIJK describing the bound state structure, and so therefore we suddenly have this NIJK describe a fusion of two elementary particles, and so now we see that the theory for the excitation is pretty non-trivial. You have this all these structures, and also NIJK certainly should be an integer tensor with a no negative entry or non-negative integer tensor. And also they should have associativity. Means that when we fuse IJ first and K later, or fuse JK first, I later, we should get same thing. You get the same, like we have 3 traps. Either we make this trap closer, or make a second and third closer. At the end of the 3 trap, you get the same thing, the same single extension. So therefore, as a rank 3 tensor, this associativity, you can go through some exercise. Means this rank 3 tensor is special, satisfy this relation. Okay. And I think that's maybe this is the main thing, is that the theory for quasi particle is a little more complicated, have this kind of fusion ring, fusion structure. And this is a fusion ring, not fusion category, you know. So they only reveal some structure we need. So there's more structures. So when adding into more structure, you get a fusion category. And so maybe next week we'll slightly talk about this other structure. Mostly I will avoid this other structure, which is called F symbol. And but I'll just talk a little bit. And then from all this, we combine with ST matrix, then we can start to have a more or less complete theory for the topological order, and which enables us to create a table for topological order. And this kind of picture is useful maybe later when you want to use topological order to describe symmetry. So those kind of things are kind of useful. So that's why I introduced here. Okay, and other questions? I will end here.
I have a naive question related to how you define topological excitations. You defined it in terms of having a ground state that,
yes,
that can turn into subspace after the excitations. Why couldn't we do that for topologically trivial systems in the same kind of, why does only exist in topological systems, this kind of description?
Actually, this is an excellent question. Actually, we can do that for the trivial system as well. Okay. But here, for the trivial system, what we have is we have a symmetry. When you have a symmetry, then you want to maintain the symmetry to see the symmetry property. Then you design your trap to be symmetric trap. And then you can have this. Then the extension defined by symmetric trap would carry property of the symmetry. And they can also fuse. You know, the NIJK can be defined. They can also fuse. They can also have other things, braid and fuse. So therefore, if you do this trap and extension, you define symmetric extension, and they have this fusion and all that. And there's a fusion category, very scary name, to describe those trapped extension. And actually, I would say this is an experimental way to describe a symmetry. So imagine, suppose you have a sample with symmetry, but the symmetry is absolute in our universe. We cannot even break symmetry by our instrument. So therefore, we can only design symmetrical trap. And this have a problem because when you only have a symmetric instrument, we cannot do symmetry transformation. Symmetry transformation breaks symmetry. So our ordinary way to look at symmetry is actually by breaking it, by looking to the symmetry. We already break it, you can look inside the representation. But if your symmetry cannot be broken, even if symmetry, even the instrument cannot break symmetry, then we cannot look into the symmetry. We cannot look into transformation. Then there's an experimental question. How do you measure the symmetry? How do you know your system have a symmetry if you both your sample and your instrument have a symmetry? And which symmetry? So what I'm describing here actually is a way to using symmetric instrument to extract which symmetry you have by not measuring symmetry group, but measuring the fusion of symmetry charge, these representations. And actually, there's a famous theorem, the Tanaka duality. By measure those fusion and of the symmetry charge, you can recover the group. So this fusion language and the group language is have same information. There's no loss information. And I will try to say the group language is a theoretical. Theory is the way to describe symmetry, and the fusion is supposed to be experimentalist the way to describe symmetry. And so actually, if you look at the, although this kind of things seems very theoretical, very fancy, something like that, but it really follow very well about the measurement. We only talk about something which can be measurable, and just in terms of those measured things. Like for example, we don't talk about the wave function. The wave function with the phase factor is unphysical. The wave function itself is unphysical. And here we talk about degeneracy. What is a degenerate ground subspace? In principle, you can use in heat capacity to measure degeneracy. Certainly very difficult. So in a sense, so this is the way actually even go beyond the wave function. You know, we don't even have this phase factor wave function to come into play here. And so it's a very physical way to describe a quantum system. And here I'm really using topological order as an example, but symmetry should be better example. Yeah. Using this way, just say, if my instrument do not break symmetry, how do I measure symmetry group? Yeah, that is the question. And then what I described, the fusion ring is a way, you by measure fusion ring, you can measure part information of symmetry group. Yeah.
In the fusion ring expression, you mentioned that the n numbers can be any non-negative integer.
Yes.
If I think of that as an accidental degeneracy between K1, K2, what does n equal to 2? How do it?
Yeah, n equal to 2 really means following. Yeah, the kind of skip is as so usually the IJ fields is became some K1, K2, K3, K4. But sometimes the K1, K2 is the same type. It's like you can direct sum of 2 spin 1/2. So here I just combine this if K1, K2 the same type, both K. I just say I say it's 2K. I just put the 2 there. So the 2 of n is not a multiply 2. It's a direct sum. It's a I don't know. This yeah. This is a these 2 really means in the sense of direct sum. Yeah, but direct sum. What do you mean by direct sum of vector space? It's a tensor product of 2 vector space. So direct sum also become tensor product. So the whole thing became super confusing. Yeah, you know this. But this is just all layer of things. Yeah. So the 2 really means the 2 copy of a direct sum of 2 of same representation. Yeah, you can actually, yeah, you can view this IJ as a representation, you know, as label representation. You know, sometimes when you fusion tensor product of 2 representation, the third representation may appear by two copies. Then you put the 2 there. Yeah. So this fusion ring just have that meaning. Yeah, I'm sorry, I'm kind of too quick here. Yeah. Okay, yeah, see you next week then. We only talk about something which can be measurable, and just in terms of those measured things. Like for example, we don't talk about the wave function. The wave function with the phase factor is unphysical. The wave function itself is unphysical. And here we talk about degeneracy. What is a degenerate ground subspace? In principle, you can use in heat capacity to measure degeneracy. Certainly very difficult. So in a sense, so this is the way actually even go beyond the wave function. You know, we don't even have this phase factor wave function to come into play here. And so it's a very physical way to describe a quantum system. And here I'm really using topological order as an example, but symmetry should be better example. Yeah. Using this way, just say, if my instrument do not break symmetry, how do I measure symmetry group? Yeah, that is the question. And then what I described, the fusion ring is a way, you by measure fusion ring, you can measure part information of symmetry group.
In the fusion ring expression, you mentioned that the n numbers can be any non-negative integer.
Yes.
If I think of that as an accidental degeneracy between K1, K2, what does n equal to 2? How do it?
Yeah, n equal to 2 really means the following. Yeah, the here kind of skip is as a. So usually the IJ fields is became some K1, K2, K3, K4. But sometimes the K1, K2 is the same type. It's like a you can direct sum of 2 spin 1/2. So here I just combine this. If K1, K2 is the same type, both K, I just say I say it's 2K. I just put the 2 there. So the 2 of n is not a multiply 2. It's a direct sum. It's a I don't know. This is a. These 2 really means in the sense of direct sum. Yeah. But direct sum, what do you mean by direct sum of vector space? It's a tensor product of 2 vector space. So direct sum also become tensor product. So the whole thing became super confusing. Yeah. You know, this but this is just all layer of things. Yeah. So the 2 really means the 2 copy of a direct sum of 2 of same representation. Yeah, you can actually, yeah, you can view this IJ as a representation, you know, as label representation. You know, sometimes when you fusion tensor product of 2 representation, the third representation may appear by two copies. Then you put the 2 there. Yeah. So this fusion ring just have that meaning. Yeah, I'm sorry, I'm kind of too quick here. Yeah. Okay, yeah, see you next week then.